Okay, so the second thing we want to talk about here is this whole concept of enthalpy. And enthalpy is something that we want to measure. We can only measure the change, and it's the difference between the potential energies of the products and the reactants. Okay, so it's a state function. So delta H, what that means is it doesn't matter. Over here, if I look at this, it doesn't matter what pathway I use to get from reactants to product. I can do it in 1 step or 2 steps or 3 steps. The enthalpy, the delta H of the reaction, is always going to be the same. Again, it doesn't matter how I get from these reactants to this product, whether I do it in 1 step or 200 steps, or what process I use, the change in enthalpy will be the same. That's what a state function means. And the important thing here is that delta H and Q are the same thing if I am working at constant pressure. Okay. And most chemical reactions are going to occur at constant pressure. So if I am running a reaction at a bench and I have the beaker open to the outside, then the pressure is going to be constant. If I had a closed system, the pressure won't be constant, right? Because there'll be more particles and they'll be banging against the walls, causing more pressure. But in most reactions, my beaker is not closed, it's open, and therefore particles can leave and the pressure remains constant. So if I have constant pressure, the enthalpy change for a reaction is delta H, enthalpy, is going to be the same thing as Q. Okay, and we deal a lot with enthalpy, delta H, which is really, we're talking about heat, right? Transfer of heat. And we can calculate it from lots of different ways, and we're going to take a look at all of those ways. Now, I will say there's a lot, first of all, there's a lot of stoic involved, and the problems that you're going to have is doing just basically a lot of stoic and treating energy as either a reactant or a product. We're going to do a lot with calorimetry. And the one thing that the College Board is really pushing to do more of is to focus on using bond energies. And we do that last in this part of thermochemistry. And you'll have a lot of practice with that. All right, so let's just take a look at how we would do this stoichiometrically. This is kind of a conceptual question and a little bit of stoic. Okay, so if I add solid potassium hydroxide to water, I get the solid becoming aqueous. Now, what it says here is I have plus 43 kilojoules per mole. Now, this is showing the heat as a product. Okay, I've got a plus, I'm showing heat as a product, which means this is exothermic, right? I'm losing, my delta H is going to be negative. The system is losing heat. I lose heat as I do this. Now, there are 2 ways to write these equations, and you've got to watch out for what you have. If it is written as a plus some number of kilojoules, either as a product or as a reactant, sometimes it'll say this plus 10 kilojoules. I'm adding energy here, which means this is endothermic, and I'm going to have a positive delta H. Okay. A lot of times you won't see this written as plus 43 kilojoules. You will see this is written as delta H equals negative 43 kilojoules per mole. Now, both of these mean the same thing. Writing it as a product or writing delta H equals this mean the same thing. Okay, so heat is leaving. So what happens to the beaker? Well, it's getting warmer, right? Exothermic reaction is going to make that beaker feel warmer. The heat is leaving, goes onto my hand, and I say, ouch, right? So if it's leaving the system, or if energy is a product, it is going to be exothermic. Okay, and then we want to know what is the enthalpy change for doing this with 14 grams. Okay, so this is where stoic comes in. So what this tells me is for every mole of reaction, now that's another thing the College Board is doing, is they're trying to go towards using units of energy, or enthalpy, as kilojoules per mole of reaction. Okay, so what this is per mole of this reaction, I get a product of 43 kilojoules, okay? And what I want to know is what happens if I only have 14 grams. So this is just simple stoichiometry. So I have 14.0 grams of potassium hydroxide. What I know is the molar mass of potassium hydroxide is 56.11 grams of potassium hydroxide is 1 mole of potassium hydroxide. And what I know based on what's given to me in the problem is that 1 mole of potassium hydroxide in this reaction generates 43 kilojoules. And when I do all my crossing out to cancel units, I end up with an answer in kilojoules. And now when I do all this, you got to be careful. When I do all this, I get a positive number in my calculator, but I got to recognize that I've already established that my answer is going to be negative, and because heat is being lost, so I can put this in here as negative, but I got to remember to do that. So my calculator says 10.7 and looks like I want 3 sig figs. It's got to be negative. So again, people look at this, easy problem. Problem is, you got to know if it's exothermic, right? If it's getting warmer, I got to have a negative. Okay. All right, so we're going to stop right there.